Okay, so now that we've seen the theory behind decision trees and different ensemble methods like boosting, bagging, and random forests, we're going to try different packages in R that allow us to train and test these different methods that we have studied. Again, remember that in the theory part, I tried to explain how these packages work internally, right? How decision trees are built, how you choose the root and the different subroots based on information gain. How can you improve like different classifiers or regressors based on using multiple classifiers instead of just one through either boosting or bagging, right? And how specifically bagging applied to decision trees, which is random forests, how these things are trained internally. Okay, now we're going to be running packages that do all these processes as a black box, but it's very important, as I keep saying in every single class, it's very important that you understand how these packages work, because then you are able to interpret the output of the packages. And then when you change, say, to another language like Python, you'll be able to understand what are these packages doing internally, because you know how these models are trained. So I'm gonna first work on an example with decision trees and how we can improve a decision tree using boosting, and then we'll move on to bagging and to another example for bagging and random forest. For decision tree and boosting, we're going to be working with a credit CSV file. This file basically has 1,000 examples of loans that have a combination of nominal, categorical, and numeric features, indicating characteristics of the loan and characteristics of the loan applicant. Okay, and the target class is whether the loan went into default or not. Okay, you will see that in the data set, the data, like some of the numeric data, is in DM. This is basically Deutsche Marks, which was the currency in Germany before the euro started to be used. Okay, and this is sort of, letters that you will see throughout the example. In this case, the objective that we are pursuing is basically use a decision tree to predict whether an applicant will default on a loan based on the different numeric and categorical features that we have in the dataset. That is, given the different characteristics of the person and of the loan, can we predict whether someone will default or not? Okay, and we want to do that by building a decision tree. And so the first thing that we're going to be doing, as usual, is to basically read the CSV file that we'll use, and then we can look at some of the characteristics of the CSV file to familiarize ourselves with it. So, let me make this smaller and let me go to here. Okay. So the first thing that we're going to do is to basically load the CSV file. Okay. Okay, remember that you have to set your working directory. So if this file is not in your working directory, you will get an error when reading the file. So remember to use the setwd command to set your directory to where this file is. Okay, and then we can basically view general characteristics of this file with the view command, which opens this table. As you can see here, we can see things like, for example, what's the checking balance, like what's the balance in the checking account of the person that has requested the loan, what's the duration of the loan, credit history, if it's critical, good, poor, what's the purpose of the loan, the amount of the loan, how much money they have in the savings account, employment, percent of income that that loan represents, and some other features. Exactly 14 different features, and then the 15th column is basically whether that individual has defaulted on the loan, yes or no. Okay, we can check different statistics. For example, let me show you a couple of commands. With the table command, we can basically create a table with the number of times that a given value appears. So for example, if you look at checking balance, right, what this table is telling you is that from all the 1,000 entries that we have, if we see the balance that they have in their checking accounts, 274 participants have, you know, a very small amount. 63 participants have more than 200. 269 participants have between 1 and 200, and then the remaining, we don't know how much they have, right? So this is one way of checking characteristics of the table. We can also look, if it's like numeric features, we can also look, for example, at summaries. So for example, if we want to look at a summary of, you know, what's the amount that they have requested for the loans, this is telling us basically what's the median loan amount, 2,320, and what are the different quartiles, okay? So, you know, these are different statistics that you can check on, and you can play with that. So the next thing that we need to do, because we basically wanna, as I was saying before, we want to train and test a decision tree. The next thing that we need to do is to build the training and the testing data sets, right? And so before we divide the data set that we have into training and testing sub-data sets, we first need to randomize the data. So sometimes what happens is that the data sets that we get are ordered by, for example, say, amount of the loan, or by a specific characteristic, okay, that we might know or we might not know about. So it's always a safe practice to basically randomize the data and then create the testing and the training sets. And what you see here, these are basically commands that allow us to do that. So the set seed is, you know, we need to set a seed every time we randomize and make it different so that we get different results, right? And then basically this credit rand, credit order runif 1000, what that means is that the runif command creates numbers between 0 and 1, okay? And then the order is basically saying, what's the order of that number? What's the ranking of that number within the 1000 numbers that we have generated? And so, for example, if you have one of the numbers generated is 0.9999, that's probably going to be rank 1. And so you're saying take the first, you know, line from the credit data set with all of the columns. That's exactly what this command is doing, okay? So we are just reordering the credit data set with a different order. The samples are all the same, but what we have in each row is going to change. So let's do that. Basically, we're going to set a seed, do whatever you want, okay? And then we're going to create a new data set that we're going to call create credit rand. And this is basically going to have in each row, it's going to have a different row from the original data set that we create using the runif command with 1000 numbers, okay? And basically, you know, whatever that runif command outputs, we take the rank and we take that row from the credit dataset and all of the columns, okay? So if we view credit rand is exactly, you know, another dataset that also has 15 columns and has 1000 entries, but the only thing is that they are ordered differently, as you can see here. Okay, and once we have that, we have randomized the dataset. An important practice when we randomize is if the only thing that we've done is that we have reordered the rows, okay, the summaries, like the different, the averages for the different features, like the, you know, medians and quartiles should be the same, right? And so a good test after randomizing is just checking that a given feature, like the summary for a given feature, is the same for both the original dataset and the randomized dataset. And as you can see here, we're getting same medians, same quartiles for the two data frames that we have created, credit and credit rand. So that means that in fact, the only thing that we have done is that we have randomized the entries. Now, the next thing that we want to do is basically split, you know, this data set into training and testing as usual, okay? And so in this case, because we have already randomized, we can just simply say, okay, take all the rows from 1 to 900 for the training data set. This is 90% of the data set, and then the remaining 100 rows, take them for the testing data set, right? So we are creating a credit train that basically takes, you know, from credit rand, takes the first 900 lines and all of the columns, and then we create a credit test that basically takes the randomized data set, and we take the remaining columns and, you know, the remaining rows and all of its corresponding columns, okay? An important thing when we divide into training and testing, if it's randomized, more or less, we need to observe that the target variable that we are trying to predict, in this case, whether somebody's going to default on the loan or not, is more or less equally distributed in both the training and the testing data set. That is, you don't want to have, for example, a training data set with all of the yeses in the default and a testing data set with all of the no's in the default, okay? Because then you are learning something different from what you are training on. And so that's, generally, it's a good practice to basically evaluate that, okay? So we take credit train, we look at whether someone has defaulted or not, and that's the proportion that we have of whether someone has defaulted or not. And we do exactly the same thing for the testing data set. And the proportion should be similar. It's not the same, but as you can see, it's quite similar. And so, you know, this is a good distribution of training and testing data set. They are randomized, and at the same time, we have a similar number of yeses and nos in the target variable that we are trying to predict. Okay. So now we're going to be using, to build a decision tree, the predictive decision tree, we're going to be using C50, that's a package. Sometimes students have reported issues installing the C50, so just make sure that you run the install packages command from that repository, and with the dependencies being true, this means that, you know, when you're running this, when the package is being installed in R, it's going to basically install all of the other additional packages that are needed to run C50. And sometimes, depending on the version, some students have reported that they also need to install this other clear package. So, you know, in case you face any issues, make sure that you install that as well. Otherwise, if you cannot install it, as usual, you can reach out to Anjali and myself. But, you know, once you have installed that package, you can, as usual, load the library, which is called C50, okay? And then, so what happens here is that, interestingly, the default parameter that we load yes, no, is not a factor, it's a character. And so we need to, the way C50 runs is that it's expecting the whatever we are predicting to be a factor. And so we need to transform that, okay? So we basically say, okay, take the training data set, okay? And then we transform this as a factor. So credit train, and we default. Okay. And now that it's a factor, we can basically run the model. How do we train this model? So the way we use the 350, which is in reality, you know, the 5.0 decision tree that we saw in theory, is that, you know, you call C5.0. Now you input, you know, the training data set, okay, except for column 17, okay, which is the column that we want to predict. And then basically the value that we are trying to predict is whether someone has defaulted or not, okay? So if we take a look at the model, basically this is telling us that you know, we are building a classification tree. For training, we are using 900 different samples, okay? And 16 is the number of predictors that we are using. And then it also tells us the tree size, okay? These are just characteristics of the model. If we want to see a summary as well of the model that we have just trained, of the decision tree that we have just trained, what this is showing, the first thing that we can explore, it's basically the decision tree that we have built, right? And so what you can see here are the different branches that we have in the tree and how the decisions are being made, okay? And something else that we can also observe is the confusion matrix and the importance of the attributes, okay? So what do we see here? You can also check it in the slides. I also added that information here, but basically, you know, we also have it here. What you can see here basically is, you know, the top of the decision tree. And so how we transform this into if-then rules, basically the checking balance is unknown, then the person will not default. If the checking balance is in any of these ranges, then we need to check the credit history, okay? And when we check the credit history is perfect or very good, and the number of dependents is larger than 1, then the tree is saying that the prediction could be that yes, that they default. Okay? And so we can go down these branches. If the credit history is critical or poor, and the duration of the month is shorter than 11 months, then that person is not going to default. Okay? And so you can go down this tree. I mean, basically, the deeper you go, the more branches you're having, and the more you are going in depth into, having different branches, and the longer the distance will be to the leaf. But basically, we can transform this into if-then, okay? And that's an exercise that's important for you to do, like try to understand how this tree looks like, at least at the top. And then something else that I wanted to discuss, another output of this decision tree model that we are training, besides looking at the tree itself, again, decision trees are extremely transparent in that we can see, how decisions are made. And so besides looking at the tree and understanding how a yes or a no to the defaulting on the loan is assigned based on different characteristics, we can also look at how well the decision tree is performing during training. Okay, so this is the usual confusion matrix, and as you can see here, the number of samples that are being classified as no and that are no themselves are 609. So whenever we say it's not a default, we say that correctly for 609 loans. And whenever we say that there was a default, and there actually was a default, whenever the decision tree outputs that the person was going to default and it was an actual default, was 166 times. Okay, so we are not doing that well here, because there's oftentimes, when a person defaulted, we are basically classifying it as not defaulting with 102. So, the yeses, like the true positives, we are not detecting them as well than the true negatives. But still, we are not doing a bad job. And then in terms of, what are the features, like when we go through the tree, like to all the depths, what are the features that are most prevalent when deciding whether someone is defaulting or not? Checking balance is definitely, 100% there. Credit history, the duration of the loan, the balance in the savings, the job, other types of credits, right? I mean, these are sort of the major variables, sort of the important variables that play a role in whether a person is gonna basically default on a loan or not. Okay. And so this is basically during training, right? So, we have, we are using this credit data set. We have built a decision tree that will tell us whether someone defaults or not. We have explored how good that tree is during training. We have explored how the decisions are made, what are the important variables. Now we actually need to do the prediction, right? So we need to use this decision tree that we have created, that we called credit model, and we need to test on our testing data set, we need to test how well the credit model is doing. Okay, to do that, we use the command predict, and then basically what you see here is the usual confusion table. Okay, so we will be using the cross table command to compute the confusion table as usual. So let me go here. Now that we have this credit model, that we have created, we are basically going to predict. So we are going to call that output credit pred. We use the command predict, and we basically say, okay, so we are going to use the predict model that we have trained to predict on the testing data set. Okay, and now what do we do? So we want to work with the cross table command. Let me copy this because it's such a long command. I don't want to mess things up. And okay, and we basically run the cross table command. Again, this is just the command that generates the confusion matrix, okay, as we've already done it in prior classes. And this is how good our decision tree is during prediction, okay? So let's look at this table more in detail. This. Okay, so what we can see here, what is it? So this is the confusion matrix during testing. And what you can see is that for 57% of the samples, when we say that the person is not going to default on the loan, we correctly predict that. Okay, so we predict that it's a no default, and we correctly do that 57% of the times. When the person actually defaults, and we predicted that that person would default, that happens 16% of the times. Okay? However, as you can see here, when we predict that it's not going to be a default, we capture most of the cases where it was an actual default. So out of the total 68 defaults, we capture most of them as being defaults. What happens with the actual defaults, okay, and we had 32 of them, is that we are, like, this decision tree is not as good as detecting whether someone is actually gonna default or not, is yes gonna default or not. We are good at detecting the the true negatives, but we are not as good as detecting the true positives. It's basically like throwing a coin, right? Like 0.5% of the time we're saying yes, they default, 0.5% of the time we're saying no, they don't default. In addition, we see that this is a little bit worse than the training, and that's expected, right? Like generally when you train a model, the testing is not going to be as good as the training, because if you look at, you know, the numbers here, and you look at the no and the yes, you can see that for the no, you know, we're doing really well, very similarly, but for the yes, okay, we are detecting a few more cases in the true positives. Okay, so during testing, you know, this is getting a little bit worse. Now, how can we improve it? Well, we've seen it in today's class, right? So we can try to improve these models by using boosting, for example. Remember that boosting basically uses the same data set multiple times, but what boosting does is that it's going to assign different weights to different samples within the data set, in a way that if a given sample was extremely wrongly classified in one iteration, now we're going to assign a higher weight to that sample, so that, you know, the new decision tree that we train is going to focus on sort of that subset of samples that performed really poorly in the prior decision tree that we trained, right? How many trees are we going to train? Well, this is something that we have to play around. I'm going to show an example where we just train 10 different trees, but, you know, you can play around and see whether having more or less trees actually improve more or not, okay? The command is exactly the same thing. It's a C50 library, command is C5.0, and we do exactly the same thing. We train with, you know, basically all of the values except for the default value. We use the default as, you know, the value that we want to predict, the factor that we want to predict. But in this case, we use the trials variable. And what that means is that we're asking the package to basically train 10 different trees and to report the final output that will be based, because this is a classification setting, will be based on a final weighted voting. Okay? Okay, so let's do that. So we are going to create a new model, which we call Boost 10. This is going to be a 5.0 again, and we're going to use exactly the same thing. So we're going to be training the model with all the columns, but except for the default. But in this case, we're changing the command that we are saying, let's run this 10 times. Okay. We can again check this credit Boost 10 model. Okay, and it gives us, you know, you've done the training with 900 samples, you have done like 10 different trees, and the average tree size across the 10 different decision trees that we have trained is 51.8. We can also check the summary, as we did as well, right? And the summary, again, in this case, I mean, we don't even have the space to explore all of these, but for each trial, for each tree, you can check the details. So this is the tree for trial 7, and you can say that it starts with the credit history and other credit, right? You can scroll up and see that we have another tree, like trial 6, that starts with housing. Okay, so you can see how different trees specialize in different things. Okay, this one starts with the checking balance being larger than or being within certain ranges, right? And so different trees will specialize in different things. And, you know, by putting all of these things together, we hope that our classification will improve, okay? What else can you see? So in this case, we don't have one decision tree, but we have 10. And what you see here are the errors associated to each of the trees that we have trained. What you can see is that the errors are between 10 and 20%, but when we boost, the error goes down to 3.2, right? And you can see here the confusion matrix and again the most relevant attributes that we are using. You can try and compare this against basically the other unique decision tree that we trained. But let's look a little bit more into, you know, this analysis. So what can we see here, right? So what we can see here, this is basically the having 10 decision trees during training, okay? We are not testing yet, but having 10 decision trees during training, and this is having one decision tree during training. You can see that the error, 3.2% versus 13%, has already decreased. And when you look at the no's and the yeses, the true positives and the true negatives, what do we observe? The true negatives have increased slightly, so we are now identifying correctly no defaults as not being defaults for 631 of the cases instead of 609, okay? But for the yes class, when we say that this is a true positive, the person is going to default, we've gone up from 166 to 240. So we are now, with this boosting approach, at least during training, we are now able to identify better the default cases, the true positives. Okay, so that's for training. Now we're going to do similarly to what we did with a single decision tree. We are going to apply boosting and see if results improve during testing. Okay, so we'll take the boosted model that we have trained for decision trees, we will run the testing data through it, and we will look at the confusion table and see whether the results have improved or not. Okay, so how do we do this? So we do create this new data frame where we are going to save the output of the prediction. We're going to be using the credit boost 10 model that we have trained, and we're going to be putting the testing data through it. Okay, and now we run the cross table command again, because this is a long thing. Let me just copy it, because otherwise I will for sure make a mistake. And we compute the confusion table with, again, this is, you know, the values, the default values in the testing data set, and this is the default values that the model has predicted, right? So we take the predictions and the actual values, and we look at the confusion table and see how well we're doing. And this is what we have in this slide as well. So what do we see here? This is during testing, right? So this is the confusion matrix during testing for a boosted decision tree, so 10 decision trees exactly. And this is the confusion matrix with a single decision tree with no boosting, right? What do we see here? So we see that the testing results are not, again, as good as the boosting, as the training, as the boosting results during training, okay? So basically we're still performing not basically like throwing a coin for identifying the positive defaults when someone defaults or not. We have not improved at all, so this is still 16% of the cases, okay? But we observe an improvement in the detection of the true negatives. So when we say that someone will not default and they don't default, we see an increase from 57% to 59% of the cases. So we are like 2 more cases are being correctly identified as individuals not defaulting. Okay, so in this case, what we observe is that using boosting allowed us to improve a little bit the performance, okay, of basically a single decision tree. Okay.